So the plan for today is that we're going to learn a bunch of collections. We call them ADTs, abstract data types. I'll explain what that term means in a minute. But this week is learning all about all the different collections that we have in our Stanford Collection Library. Homework 2 that goes out on Friday is going to be using those libraries to solve different programming problems. And unfortunately, we only have 2 lectures this week to talk about this material. We had an important holiday on Monday, and so we lost a lecture. So I'm going to go a little faster today through some of the content, but hopefully we'll catch up. One course announcement I wanted to make is that we have a form up about our exams. So you don't have to come to these lectures. I'm so glad that so many of you did come to class today, but your lecture attendance is not part of your grade. But I do need everyone to come to the exams on their scheduled dates and times, unless you have an approved conflict, like an athletic event or something like this. So I'd like you to go to this form, everybody, individually go to this form and just submit whether you're able to come or whether you have a conflict so that we can make sure we know everybody's status. I want you to do that by a week from Friday. I'll remind you more times closer to that date, but anyway, that's up. In the meantime, you're also going to have your sections start this week. Have you guys gotten a message about what section that you're assigned to? Yes. No? Yes? Oh, wow. Okay. Well, hey, you do have section this week, and somebody assigned you to a room, although maybe somehow you didn't get a message about it. Some of the sections are today, so you should go check and see. You should have received a message. What you should do is, if you don't have that information, if you go to the CS198 website, cs198.stanford.edu, that site has a login, and if you log in there, it should give you some information about what section that you're in, including the date and time and room, and who your section leader's name is. So if you're not able to find that information on that website, please contact me and the TAs by our email contact information on the webpage, and we'll help you, okay? But please double check that today if you don't know that, because some of you have section later today, okay? All right, so anyway, like I said, we're going to learn about collections today. So let me open up my slides. And this all comes from chapter 5 of the textbook, if you want to read along. We talked about vectors a little bit last time. I'm not going to spend a ton of time on vectors because I think every language has a collection like this. And so you guys, I'm expecting, have seen something similar to this in your own previous programming experience. Like in Java, they have the array list. That's almost identical to what this thing is. In JavaScript, you have an array or a list structure that's basically the same. Most languages have this kind of structure, a list of elements that have indexes that start with 0. And so you can declare a vector, you can add elements at different indexes. The vector sort of shrinks and grows to fit the elements that are inside of it. You can access the elements using square brackets. So we've talked about that already. Here are the methods. I've already shown you this. I'm not going to linger on this slide. One thing that we've seen with these kinds of structures is you can insert or remove elements from different points in the structure. And if you add things at the end, they're just appended, but if you add things at the start or in the middle, it shifts things over to make room. Similarly, if you delete something, it shifts everything over to make room. If you want to delete something without shifting, like for example, if I don't want this 8 to be here anymore, but I want to leave that slot blank, there's not really a way to say that. I mean, I guess you could replace the 8 with like a 0 or something, but you can't like delete the 8 and have nothing be there. There has to be some kind of value there, even if it was just called 0 or something like that. Some of you have heard of a special value called null, but null is not an int, so you can't put null in this case. But anyway, one thing we're going to talk more about on Friday is the efficiency of some of these operations. And I mentioned this briefly last Friday, that this shifting takes time. So like if you delete the first element of the vector, it has to shift all the other ones over. And each element that you shift takes a certain amount of time to do. And so the bigger the vector is and the more elements you're shifting, the more time it takes to do an individual insertion or deletion, right? So sometimes that affects how you should write your code. If possible, you'd like to mostly add things and remove things from the end of a vector rather than from the front. You can't always write your code that way, but you'd like to if you can, okay? So do you have any questions about that? Does that kind of make sense about the, make sense about the No, now I'm doing it. No. About how the vector works, about how this shifting works. You can have nested collections. You can have collections of collections, such as a vector of vectors. So here I have a vector of vectors of ints, and then I add 3 vectors to my vector of vectors. And so I call the individual vectors rows, and then the overall thing I called VV. So it's a little bit like a grid, because you can access the elements in there using 2 square brackets. That looks a lot like accessing a grid, right? What would you say is the main difference of this versus a grid in terms of what it can or can't do? Bless you. Yes?
All the rows in the grid are the same,
Yeah, a grid has to be rectangular. All the rows have to have the same number of columns. And this thing could be non-rectangular. This particular one, I guess you'd say, was more triangular. You could have rows of different lengths. So, some pros and cons. I will say another difference that's more just, nitpicky is that the syntax, you have to write more lines of code to declare this thing, initialize it. But yeah, I think your answer is the best one, that this one allows a non-rectangular shape. But I just wanted to make this overall point that you can have a collection inside of a collection. You could have a collection of collections. That's allowed in C++. Okay? All right, so I'm actually not going to talk more about vectors just due to time because we lost our Monday lecture. But I want to talk about another collection called a linked list. Now, I think it's going to be hard for me to motivate why you would be interested in this collection because it does exactly the same things that a vector does. It's a collection of elements that have indexes that start from 0. And you can insert things, you can add things to the front or the end or the middle. So in terms of like what you would do with it, what kind of problems you could solve with it, it's identical in that sense to a vector. It lets you do the same things. But the difference is, internally, the way that the list stores the data is different. With a vector, it has a big brick of memory, which is basically an array, where it stores all the elements that you have added. With a linked list, it actually makes these little objects called nodes that sort of connect or link to each other to form a chain. We're going to talk a lot more about that later in the course. It'll be your favorite thing. It's called pointers. You'll love it. Ask your friends in your dorm if they love pointers and see what they say. Anyway, it's got a different internal structure, how it stores the data. Now, you don't have to worry about that very much for now, but that internal difference has some ramifications that might affect your code if you use this thing. So if you want to insert or add something into this structure, I just talked a minute ago about with a vector, when you insert something, you have to shift the elements over to make room. With this structure, you do not have to do that. If you decide that you want to insert a value 42 at index 3, you just find that spot in the list and you just link it in, you just attach it. There's lots of different analogies for a linked list. It's almost like each little box is a person's phone, and the arrow to the next box is like you've got the next person's phone number in your phone or something. And so you sort of call, what if you wanted to tell everybody that there was going to be a party? You're all going to go to a rollbly because it's lit? Is that how you say it? So you have to call each other, because it's 2000 and not 2018, so you have to call people to tell them that there's a party, right? So the first person calls the second person, and they call the third person, and so on. If you want to introduce one more person into the social circle, you could just have one of the people call them and then have them call the next person, and you don't need to do any more work than that. So that's interesting. That means that this structure can do certain operations more efficiently than a vector can do. But as a trade-off, this thing is slower at certain other operations. So like, for example, it uses more overall memory than a vector does. And it's not very good for looking at the nodes in certain orders. Like if you want to just jump around to random elements and just look at their values, this structure isn't very good for that because the way that it looks up values is it has to start at the beginning and sort of walk over until it finds a value. And so that takes time if you have a large list. So anyway, my point of showing you this structure, I don't think you need to use the linked list library very much in this course. But I wanted to talk about this idea that sometimes you can implement the similar structures with different internal storage, and they have different pros and cons. So that idea of different ways of implementing the same operations is something we also call an abstract data type, ADT for short. So an ADT basically just means a set of operations that you want to be able to perform. I want to be able to add and insert and remove and ask for the size and clear. You want these different methods basically. So any object that supports those methods, you could say that it implements that set of operations. It implements that abstract data type. So a vector and a linked list both support the same abstract set of operations. We might choose to call that set of operations the list operation. So that's interesting, and we're going to come back to this theme, this idea, a lot in this class. We're going to, see a structure, we're going to use it, we're going to say, wow, that's really helpful, I like that. How does it work? Well, maybe we'll learn 1 or 2 or 3 different ways that it could work internally and see their pros and cons. Often having to do with efficiency trade-offs, memory usage trade-offs, that kind of stuff. Okay? So that's what an ADT is. I want to show you some more collections that come with our libraries for a while. And I want to spend most of the rest of class talking about 2 structures called stacks and queues. So now these are interesting structures because they are not as powerful as vectors and linked lists are. They don't support very many operations. So I think as like a salesperson, I have a hard time selling you this product because you're going to say, I don't think I need this product. I already have vector, I'm fine. So the pitch is tough for me, But I guess the sales pitch is the following. It's like these structures don't do very many things, but the things that they do them pretty well, they do them efficiently. And so sometimes, we're going to see this with some other structures this week, that sometimes less flexibility means more efficiency or more power in other ways. Okay? So what these structures really do, let's talk about the stack first. A stack is a collection. Conceptually, you think of it as elements being stacked up vertically on top of each other in a collection. And when you add things to a stack, you always add things to the top of it. So if you add values like 1, 2, 3, 4, the 4 was the one you added the last, and so it's at the top of the stack. Now, if you want to look at the elements or remove elements or something like that, the stack only allows you to access the top of itself. I think in a lot of real-world analogies, like the plates at a cafeteria, when you go to grab your plate or your tray to get your food, it's a stack of plates, and you don't usually reach in there and grab the 10th one, you just grab the top one, because it's hard to get in there and get the other ones, right? So that's kind of the analogy here, is you always touch the top one, the top element of the collection, when you're adding or when you're removing. And we use different terminology when we talk about adding and removing from stacks. We say that when you're adding to a stack, you are pushing a new element onto it. And when you're removing an element from the top, we say that we're popping it off. There's also an operation called peek, which means I'm going to look at what's on top of the stack, but I'm not going to remove it. I just want to see it, maybe look at its value and use it for something. And that's it. That's kind of like all this thing knows how to do. It has a few other methods, like there's a stack class that you can include into your project, and it has those methods push, pop, and peek. It also has other methods like isEmpty or size. And I don't know if I don't think I listed it on the slide, but you can print out a stack to see out or something. And you can see what it looks like inside. But that's it. That's all it supports. These slides say O1. I'll talk about what that means on Friday. Basically, it's shorthand for these methods run really fast. In terms of like, why would you want a structure that's so simple, that does so few things, when we've already got vectors and grids and things that are more powerful than this? Well, there's a lot of problems that basically work well with this style of data access. Like, if you're building a programming language, if you're going to write your own language or write a compiler for a language, a lot of times that involves stack-like algorithms. Like if you're evaluating expressions, x plus y times z, you often will push things and then pop them, and you'll use that structure to evaluate the expressions. Also, if you're running function calls in a program, function A calls function B, calls function C, the functions that get called, they actually make a stack of memory about each function. And when you return, it pops the last function off of that stack. So stacks appear a lot in computer science. Maybe my favorite use of a stack is the undo stack. When you have an app like word processor or whatever that has an undo feature, basically the way that that's almost always implemented is they have a stack of actions. Like you type some text, that's an action. Then you made it bold color or bold font, that's an action. Then you change the alignment to center. That's an action. Now you say, uh-oh, I want to undo. So it goes to the last action, the one that's on the top, and it pops it off and it undoes that. And you say, oh, I don't like that bold font either, I'm going to undo again. So it pops the last action off again. So I think undo as a stack is an example I like. So anyway, stacks appear a lot in computer science. These are the methods and operations that a stack supports. So here's a quick example. I make a stack and I push 3 values. The toString is a little confusing because we don't like to draw it as a vertical string because that would take too many lines, you know. So we draw it left to right, where the left is the bottom and the right is the top, because we just want it to fit on one line. But anyway, the stack looks like this as you add the elements to it. The last one added is on the top, on the far right there. When you pop things, it removes and returns the top value. So this first pop, it removes and returns the 17. Then I do peek, it returns without removing the current top element, which is -3. And then here last I pop, and the -3 comes off, but now it's actually been removed from the stack as well. Okay? So there's a couple things that students often try to do with stacks that don't work. So one simple thing that you can't do is to access the elements by indexes with the square brackets. That bracket operator does not work with stacks. That kind of loop, go from 0 up to size, access element I++, it doesn't compile. I mean, it's against the nature of a stack. The stack doesn't want you reaching under the bottom of the stack and looking at the arbitrary elements. It only wants you to look at the top one. So that kind of code doesn't work. So what do you do? If you want to look at all the elements of the stack, what do you do? What do you think? Yes?
Pop them one by one.
Pop them off one by one and just look at them and keep doing that until there are no elements left. So a more common idiom is the following: while the stack is not empty, pop the top element or peek at it and do something with it, right? One side effect of doing that is that when you're done with the loop, you lost the contents of the stack. You know? I don't know what the real world analogy would be if it's like you said, hey, how many plates do we have at the food court today? Well, 1, 2, you break the fuckers and then you're done. Well, we have 12. We have 12. I mean 0, because I broke them. I don't know. Anyway, you empty out the stack doing this. You have to be careful. Now, of course, you might say, well, wait. How about instead of popping them off, I'll just peek at them, because peeking at them won't remove them from the stack, right? So what if I just said, while not empty, peek? It's a good idea on the surface, but of course the stack will never become empty unless you're popping things out, right? So yeah, the loop doesn't finish without the popping. So we have this issue of like, how do I look at a stack without destroying the stack? We'll talk about that, but that's an issue. So I wanted to show you some code that uses a stack, and I just wanted to kind of have you trace through it in your head or on paper or whatever and see if you can figure out the output. So take a look at that. If you want to talk to your buddy for a minute, that's cool, and then I'll call somebody to help me answer it. Go ahead. Maybe I'll see if anybody wants to help me out. If you're not done yet, that's okay. I just got to kind of keep things moving. Somebody brave wants to tell me what the right answer? Yeah? D. I don't know. I forget. I didn't write down what the right answer is. But I'm sure we can figure it out together. So we make an empty stack. Wait, here's what I'll do. I'm a visual person, right? So let's make a text box here. So we push a 7, and then on top of the 7 we push a 10, and then we peak, so the output of that is going to be the 7, or the 10, right? Because it's a 7 the second time, right? Okay. So you know at the end of the quarter they make you guys evaluate me? One of the questions is going to be like, how much do you think the instructor knows the course material? I want you to not think about that moment right there when you answer that question. So it's a 10. So actually, just knowing that the output begins with 10 is going to eliminate answers A and B already. You said D, so let's keep going. So we did peak, which prints the 10. Then we do pop, which also prints the 10, but it also removes the 10 from the stack, right? So now the stack is just a 7. Now we push a 3 and a 5, so the 3 goes on, and then a 5 goes on, right? And then we print the pop result, which is the 5, but that removes the 5. Now we ask for the size. The size should be 2. So, right, I mean, I think it goes on from there, but I think I've got enough of a unique I think I agree with you. I think you're right. So the answer is D. Thank you. So, yeah, I mean, basically, this is how a stack works. I didn't have any loops on this slide. A lot of times when you have stacks, you're going to have like a while loop or something, and maybe we'll hit that next in a second. So let's write some code together. I want to use a stack to check whether the parentheses and brackets in a piece of code are balanced. You know, your IDE, your software does this, right? Like if you open the wrong number of curly braces or close the wrong order of braces, it'll give you an underline or an error message or whatever. So we could do kind of a very simplified version of that same process. What I'm going to do is I'm going to pass you a string, this kind of ugly looking string that's supposed to represent a piece of code. And it looks all mushed together because I want it to fit on the slide, but you could imagine it had different line breaks or whatever. But I'm passing a string of code, and all you care about is the parentheses and the curly braces in the code, okay? And what I want you to do is look and see if they match properly. So curly braces matching properly means the following. If there's an opening parenthesis or brace, there needs to be a matching closing one somewhere else later in the code, right? And the order in which they're open and closed should mirror. So like if you open a parenthesis and then you open a curly brace, you have to close the curly brace before you close the parenthesis, right? Otherwise the closings are out of order. So I want our code to check that. Anyway, the overall behavior of the function is it's supposed to return, if there's any problems, it should return the int of the character index at which the error occurs. And if there's no error, it should return -1 to indicate the string is fine. There's no error. Okay? So this says it's a stack exercise. How does a stack help me solve this, do you think? Ideas? What do you think? Okay, I think that's a really good idea. He said when you see an opening parenthesis or an opening curly brace, maybe we could push those characters into a stack so that we remember them so we know we need to match them later. And then when we see a closing parenthesis, maybe we pop, it sounds like pushing is opening and popping is closing. And I think that's a good general idea for an algorithm. So let me go to my Qt Creator. If you want to try along, this is zip files on the website, or you can use the Code Step by Step website. So I'm going to write in this stack file here. So I've got a main that tests with some different code, and it says what I want the right answer to be. And then I've got our function just empty, ready to fill in, okay? Oops, what happened there? Sorry. Okay. So you said push the opening characters, and so I think I can sort of get us started here. For each character in the string, that means for each index I from 0 to the code length, the character C is code bracket I. So I want to look at character C. I think what you said was if C is an opening parenthesis, or C is an opening curly brace, you want me to put it in a stack. So I don't have a stack yet, so you want me to create a stack of what type? Like just store these characters here maybe? Stack of characters? Stack? Okay. Let me double check if I've included the stack library. I have. Okay. So you want me to do stack.push the character C. So then else you're saying like if it's a closing one, you want me to if it's a closing parenthesis or it's a closing curly brace, then what do you want me to do? Pop? You want me to do stack.pop? Seems like it's kind of the idea. We're missing a little more. Can somebody help me write a little more code? Yeah.
You want to first peek at it and make sure that you want to pop it off if it's opening, or if it's an opening parentheses bracket first. So first we peek, and if it's an opening one, then we pop it off. But otherwise.
So first peek, and what am I peeking for? To see if it's an opening character? Well, but I think they're all going to be opening characters of some kind, right? I'm only going to push opening things that need matching later. So,
If it's the same one.
oh, if it's the right kind. Okay, right. So let's say the stack stores a parenthesis, a curly, and a parenthesis. And then down here, if I happen to see, a closing parenthesis or whatever, I want to check that this matches with the top of the stack here, right? So I think that's what you're saying. So, okay. So maybe in that case, maybe I'll separate these for just a minute. Like that, because maybe what I want to do is slightly different. So if it's a closing parenthesis, I want to say like if the stack.peak is an opening parenthesis, that's good, right? That means they match. So again, what the function is supposed to do is it's supposed to return the int of the index where there's a problem, right? And so maybe in this case it makes sense to write our code the slightly other way, to say, well, if what's on the top of the stack isn't an opening parenthesis, that's a problem, right? So I should return that this is where the problem is. What do I return here? Int I, this index of the string is bad. The character at this index doesn't match properly, right? So similarly, if you have a closing brace and it isn't an opening curly brace, that's also a problem. And I think in both cases, you want to sort of pop, right? Like I guess what you could do is you could say, if it is the right kind, then pop it off. But else it's bad, so I'll return I. So I guess I could do something similar, but this one down here uses that brace instead, right? Kind of. If they match, pop. If they don't match, return that this is a bad index, right? Okay. And then if we get down here, if you get all the way to the end of the string, there aren't any problems, so you should just return -1. So maybe that's okay to put outside at the bottom of the loop there. Let's try it out. I've got some test cases it's going to try to run, and it's crashed. I blame myself. I apologize. So this case says that it passed. It says there's a problem at index 14, which is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So that closing curly shouldn't be there because the opening parenthesis matches, right? So that seems like that's working for that case there. Then it crashes. It says attempting to peek at an empty stack. So I don't know if I really said this earlier when I was describing the stack, but if you try to pop or peek and there's nothing in the stack, it crashes your program. You can't do that. You have to check first. You have to avoid that by checking whether the stack is empty or not. Okay? Why do you think this code is crashing? Well, it might have to do with what the second test case is. So let me go look at the main and see. The second test case is this one. So it looks like this part of the string is balanced. This part of the string is balanced, but then I get here. I think it's crashing right there. Do you understand why? It's a closing bracket. What is on our stack at that point? Nothing, right? And it sees a closing brace. So let's go look what our code would do. If you see a closing brace check if the peak is matching, right? So do you understand that that test case, we have an empty stack at that moment. We're trying to peek it. So what's the fix? You have your hand up? Go ahead. Sure, if the stack size is greater than 0 and it has something on top. Right, I like to say if it's not empty, I think that looks cleaner, but that would also work fine. So I like to say is empty if it's not empty and the top element matches. So maybe I'd also put that here. I realize that this is kind of redundant with this, and we'll think about that in a second. But let's run it again. So now actually much more of the code is running properly. This one is passing, and this one is passing. This one is failing. What's wrong with that third test? So there's the string right there. Our code is returning -1. It says there's no problem. But my tester thinks that that's the wrong answer. Why is that wrong? What's unbalanced about the braces? Yeah.
Well, you have an opening brace, but no closing brace, and you're just checking basically that they always have the closing brace always matches. So I think you have to check if the stack still has anything on it at the end.
Yeah, that's a great answer. Thank you. She said, I'll repeat, that we're just checking for matching to make sure nobody matches incorrect order, right? That's good that we're checking that. But there's another thing we ought to be checking, like you said, which is that everybody who gets opened has to be closed at the end at some point. And so this code that we've written so far doesn't check that. And I think what you said was a great way to fix that, which is at the end here, we've finished looking at all the characters of the string. And so what should be true at this point, if the string is going to be valid, is that everybody who got opened got closed, which means that if the string is good, what should be the contents of the stack here? If the string is good, stack should what? It should be empty. Everybody who got open should get popped back off. That's what you said. So basically here, I think what I should do is I should say if the stack is empty, I'll return -1 because the string is a good string. Otherwise, it does have an error. The way that I think the problem spec wants us to handle this is if any braces are never closed, return the length of the string, indicating like the problem is at the end. So this is bad, so we'll return code.length, the length of the string. Okay, so now we pass all the different test cases. So hooray, we did it. So anyway, I just wanted to code with stacks a little bit with you guys so we could kind of see how stacks work, see how they behave. Do you guys have any questions about the code that we wrote? About stacks in general? About life? About anything? In the back, in the red. Oh, is that you, Zach? What are you doing? You're my section leader. Why do you have a question?
That second test, they said it passed, but it wasn't balanced because there was a buzz for the brace.
Oh, wait, it's not balanced? Wait, did I do something wrong? I'll run it again. You said this one. Oh, so, okay, you're right. I was going to move on, but there's still a bug. Good thing you came to class to correct me. So this string is actually not balanced, right? Do you understand why? Because like this part's all fine, but then when we get here, this is a closing brace where there's nothing that we opened. Do you know what I mean? So like this is no good. So we shouldn't pass that. So what do you think? What's wrong? What should I do to fix it? Sorry, who said that? Raise your hand. I didn't hear what you said. Did you have a comment? Yeah.
Yeah, you're just saying, isn't the pass fail just saying whether your code is successful? It's not actually saying whether. But you got the index right.
Oh, I did get the index right? Oh, I'm sorry. Okay, so this is saying that the bug is on index 20, which I think is here. And so it's saying we passed because we correctly identified that it is a bad string at index 20. Okay, so actually he's just wrong. Go away, Zach. That's okay. No, you got to test the tester sometimes. You got to check to make sure the tests are right before you never trust me and my test code without looking at it more carefully. Yeah, so I think we did handle that actually. If we see a closing brace and there's nothing on the stack, our code flags that as an error, because that would hit this. It would say if I see a closing brace, if the stack is empty, it'll go down here and it'll say that index is the bad index. So I think we're okay. Anyway, any other questions about the stack code? Yeah.
The pop function removes the top of the stack, but it also returns the value. So how does that work if you're not assigning it?
Yeah, the question was, if you pop the stack, it also does return the value, but I'm not storing it anywhere. If you don't store it, it just kind of discards it. But if I want to pop it off and save it and do something with it, I can say like, char top equals that, and I can do something with top. In this particular instance, what I did instead was I used it by peeking at it, and then I popped it. So, you don't have to store what's returned from pop, but you can if you want to. Okay, well, I want to cover queues. So stacks, the thing is, there's not a lot to them, but these basic operations that they support, push, pop, peek, is empty, it does all those things really quickly, really efficiently. So I talked about vectors and how they have to shift, and that can take a while. There is no operation that you can call on a stack that will be slow on its own. So that's good. It only has a few operations. It does them really fast. So let's look at another structure called queues that are a little bit similar to stacks. A queue is like a line, a waiting list of people, like at a restaurant or a lunch line or something like that, where elements are added and they get put in line. And if you add another element, it's put in line behind the existing elements. And then if you want to remove something from the queue, you remove the element that's at the front of the line. So you add to the back of the structure, and you remove from the front of the structure. The way we draw the queue, I guess my hand motions were backwards really, because the way we typically show it on the screen is that we have the front at the left and the back at the right. So if you add, it goes over here, and if you remove, it comes over here. But these are the operations that a queue supports. You can add something, which is also called enqueuing. You can remove something, which is also called dequeuing, and you can peek, which is looking at the front element to see who would come out if you did a dequeue operation. So as you can see, this really is a lot like the stack, right? The major difference is that the stack, the adding and the removing are both from the same side, the top. The queue, the adding is on one side and the removing is on the other side. So it has that slight difference to it. Okay, so why would you want a queue? Well, there's lots of tasks in computer science where you would want something like this. An example I think of a lot is like if you have a printer and different people send jobs to the printer takes a while to print each job, and so it has to queue up the jobs, and it just handles the jobs in the order that they came in. There's lots and lots of things like this. Network routers, they have a set of packets of data they want to transfer, so they have to queue them up so they can send them all out one at a time. All kinds of examples. All the presents you order on Amazon, they get put into a queue of people boxing them up and so forth, right? So this is a structure that's useful. Now, again, I think the sales pitch is hard because you say, wait, a list of things, a queue of things, isn't that just a vector? Like, why don't I just use a vector for this? So I ask you that question. Why don't I just use a vector? And if I want to enqueue somebody, I add them to the end of the vector. And when I want to dequeue somebody, I remove them from the start of the vector. Why don't I just do that? What do you think? What do you say?
Kind of like you said before about speed with the queue, they don't have to shift all the elements back when the vector is doing.
Yeah, he said the shifting the speed. If it were a vector, if I were constantly removing people from the front, I'd have to shift everybody over, and that takes time for the vector to do that. So I guess I haven't said this explicitly, but the queue does not have to do that. The queue is built in such a way that when you want to enqueue or dequeue somebody, it can do it very quickly. So a vector is actually a bad choice for those kinds of tasks. A queue is better. So anyway, those are some of the places that you might want to queue in a program there. But let's look at the actual coding with queues. There is a library called the queue class. You include queue.h, and it has those operations that I listed before. It has enqueue, it has dequeue, it has peek, it has isEmpty and size, and you can print out a queue if you want. So here's a quick example. You make a queue, you add some elements. This code is meant to look a little bit like the stack code from a couple of slides ago. You enqueue some elements, and then if you print out what happens when you dequeue, you'll get the front element, which is 42, the one that you added earliest. And if you peek, you'll get the person at the front of the line without removing them. Okay? So I talked before about how you don't access the elements of a stack with brackets and indexes. That also is true for queues. You cannot reach into the middle of the line and extract out an element and look at it. I talk about how a queue is like a waiting line, like you're waiting in line for lunch. And then I always think of, I went to school at University of Arizona, and I was in line at McDonald's once. And then this big dude comes up, and he just gets right in front of me in the line, because I'm pretty close to the front. He just like jumps right in front of me, and I'm like, hey man, who do you think you are? And he turns around and he goes, I'm Gilbert Arenas. I'm going to the NBA next year. Fuck you. And I was like, wow, Gilbert Arenas. Go ahead. You can totally cut in front of me. And I was like so excited, and I was like, you guys, the star of our basketball team cut in front of me in line. It was so cool. And my friends are like, wow, great. But there's no Gilbert Arenas provision in the Stanford queue. You can't cut in. You have to go to the back of the line, Gilbert, just like everybody else. And I get to go first because I'm at the front of the line. No jumping into the middle, no inserting in the middle, no removing from the middle. Always add at the end, remove from the front, no matter what. So if you want to look at the elements of the queue, to even just loop over them, you have to similarly do a different style than you do with a vector. The most common way is to say, while it's not empty, dequeue the front person and do something with them. And again, you cannot just use peek because the queue will never become empty unless you're removing people from it. But you might find that restrictive and say, geez, I don't want to lose my people to look at them. But most of the times when you're using a queue, it's because you want to pluck people out and process them and then be done with them. That's the point. And so you don't need to keep the elements around necessarily. You know what I mean? When the places you actually want to queue, this doesn't end up being really that much of a problem. There are some cases we'll talk about where you want to save the size of the queue as a variable rather than looping until it's empty. One example would be if you want to print all the elements out, but keep them in there. What you can do is pluck them out, print them, and then add them again, something like that. But anyway, sometimes you have to keep the size of the queue as a variable. To illustrate that, I want to jump to a question called mirror. There's other problems. If you want to practice more, there's some problems in the Code Step by Step website. But this mirror problem is I'll give you a queue of strings, and I want you to modify the state of the queue so that when it's done, it contains the same strings in the same order, followed by those same strings again in reverse order. Okay, that's what I want. So if you go to the Qt Creator project for today, I have a file called queues.cpp. So what I'm going to do is I'm going to rename main from here so it doesn't run that one. And I'm going to open up my queue file here. Okay, so what I want to do is I want to write this. Oops, wait, I have the code in here. Don't look at that. Darn. I have the answer in the file. Oh, and now it's gone. Okay, so I'm passing in this queue by reference with the ampersand. That means if I modify it here, the main will see the changes, right? So we usually pass these things by reference. So I want to mirror the contents. Do you have any suggestions? How do we get started on this? Yes?
So you dequeue and then put in the stack and pop it.
Okay, so you said to use a stack to help us. Yeah, a lot of times when you're doing a problem that involves a stack or a queue, a helpful structure to use is another stack or another queue. That can often help you to solve the problem. So you're saying I want to make a stack of strings called stack, and then what do you want me to do? You want me to move the contents of the queue into the stack? So like, while the queue isn't empty, pull something out of there, string s equals q dot dequeue, and then add that into the stack, stack dot push s. If you like to mush things together in one line, you can take this, oops, what did I do? You can take this here and cut it and paste it like that. I don't know if that line is hard to read for you, but it's like dequeue something and push that dequeued object into the stack. I'll put it back to the two-line version, but you can mush that together into one line. Okay, so at the end of this code, the queue is going to have nothing in it, right? And the stack is going to have A comma B comma C with the C on the top, right? My eventual goal is I want ABC, CBA. If I just take the contents of that stack and I put them all back into the queue, what will I get? Like if I do while the stack isn't empty, string s equals stack dot pop. So here I am using the return value for pop here. And then I do q dot enqueue s. What's the net result of all that code right there? Yes?
You're always going to get the back half, so you're going to get the reverse, but you're not going to get the initial part. So you should, instead of doing while Q isn't empty, you should predict the size and then pop it, put it on the stack, but also requeue it at the back, and then when you push everything back on the beginning, get the refresh on that.
I think that sounds great. There's a couple things to unpack there. So you said you think what this code does is it produces this, the reverse of the original queue. Let's real quick verify that. I can just run this, and it should, oops, I don't have a main because I called it main queue there. Okay, so let me try it again. So before ABC, after CBA. So what you said there was totally right. Okay, now you suggest a way to fix it. Now, I'll do that in a second, but I want to do something else first, which is, if I want the forwards version and the backwards version, I used to have the forwards version at the start, right? So what some students will do is they'll say, hey, I know, q string backup equals q, and then like down below, they'll sort of take backup and they'll add q to that, and now they have the whole thing, and that sometimes is fine, but I think a more interesting challenge would be, could I solve it without introducing another auxiliary structure? And you've added a nice way to do that, which would be, as I'm pulling the elements out of the original queue to put them in the stack, I could simultaneously also put them back into the original queue. So then down here, I want the state to be that I have A, B, C. This is the front and the back here, and this is the bottom and the top here. So if I can get it to that state, then this second while loop will dump the C and then the B and then the A. So I think I'll have the desired outcome. So a naive way to achieve what I'm trying to get here would be to say, well, push S, but also q.enqueue S as well. Put them back in line, right? There's a small problem with that, which you already said. I'll give you a second to look. Do you see the problem with this piece of code, which I know isn't what you told me to do, but you see that this doesn't quite work, right? What's wrong with this? Yeah? If I remove someone from the queue and then put them back in the queue is not shortening. So I'm never going to get empty. My loop will never finish. And you already spotted that. So say again, what's the fix for that?
So find the size of the queue at the beginning, and then for loop while and use the size of the queue as your max, and then every time push it to the stack still.
Right. You said if there's 3 elements in the queue, I need to do this remove and add 3 times. Whatever number of people were in here, that's the number of times I need to do this. I know we're about to be out of time. Size equals q.size, and then for I equals 0 through size, do this that many times. And now at the end of our program, ABC, CBA. Great job. So I'll stop there. Check your section times. Go to your section this week. I'll see you guys Friday. Thank you.